That works.
Yeah, well, let me go ahead and start off by saying thanks for coming out tonight. All the people that are here on their first CJUG meetup. Try not to bore you guys so much you don't ever come back. And thanks to Chris and Lending Tree for giving us this space. Cool. So I think obligatory introductions are probably called for here. So let me just see if I can. There we go. All right. So my name is Ty Brooks. I'm a software engineer. I mainly work in Java, do backend service type stuff. Got a little under 6 years of experience. So like I said, backend services, do a little bit of work across the stack though, and I'm interested in sort of modern architectural patterns, microservices, all that kind of stuff. And we've been sort of, I work for a company that has a sort of like an older code base, so we've been driving this whole like migration of monoliths to microservices, and kind of the same thing that a lot of you guys are into, I suppose. The company I work for, Sovereign, is an ad tech company. They're based out of Boulder, Colorado, in San Francisco, and basically are what's known as like an SSP, which just basically means they work closer to the publishers that have display ad inventory to sell. Also the volume. Okay. Anyway, so yeah, ad tech ecosystem is kind of crazy. It's pretty convoluted, but I work for a team that's more oriented towards affiliate marketing. I think the real question though is like, why the heck is my picture on this slide? I'm like right in front of you guys. You know what I look like. So mostly just because I don't write bios, and it's kind of a little trick to avoid having to write more stuff about myself. Okay. Anyway, so this presentation came about as a result of a project I've been doing at work. So we've been using Kafka for the use case is still pretty small. It's relatively, maybe a little bit bigger than a proof of concept, but still just kind of one data flow that we've converted from sort of like a, like ad hoc Java solution that's just sort of like thrown together to using Kafka and standardizing with Kafka. And so I think what I'd like to do tonight is basically share some of the research, some of the things I learned, in the research phase of that project. I think Kafka is a really cool technology. It's really interesting. I think a lot of enterprises are using it today to handle large-scale data flows and data streams. So I think understanding the theory behind Kafka is going to be interesting and helpful. And my goal today is really for people, especially who maybe aren't as familiar with Kafka, that by the end you'll be able to at least have more grounding so that you can evaluate it as a potential option or potential solution to the problems you might run into at work. So that's sort of the idea. If we have time, I'll do a coding demo. Honestly, when I've kind of run through this, it's gone a little long. So I'm not sure if we'll get around to that. Regardless, the demo will probably be me yelling at the computer for 15 minutes. So not sure you'll miss too much there. Anyways. So this talks about streaming, right? Streaming architectures. But I want to start somewhere that's maybe a little bit counterintuitive to talk about the theory behind the role Kafka is supposed to serve. So who here has heard of the acronym ACID? Yeah, so probably a good handful. So ACID is a set of properties that define certain guarantees maybe that your database gives you. So it's a database term. And we're going to start by talking about databases a little bit. Anybody, out of curiosity, can anybody name the four terms off the top of their head?
Yeah.
I think if you'd asked me before this, I'd say atomicity, consistency, whatever the heck I stands for, and durability. So I did have to look at its isolation. And just to as a reminder, so the properties that the database is going to give you. So atomicity is the idea that if you have a write to a database, the write is going to succeed or fail together. So maybe as an example, let's say you have a table that's a user, and you've got first name and last name. So one aspect of atomicity would be that if you update a row in that table and you try to update first name and last name together, first name isn't going to succeed while last name fails. Or, advocacy also refers to transactional guarantees as well. So anyways, there's this whole set of properties. You have consistency, which is related to your system eventually updating and reflecting the state of the writes. You've got isolation, which has to do with whether transactions and writes kind of step on each other's toes. But its durability is the concept that I want to talk about, and it's going to lead us to an idea that's going to be helpful to understanding Kafka. So durability is the notion that if you have a write, your database acknowledges the write, you commit your write, that write is going to stay written, right? That's durability, is you're not going to lose data. And it's really important, right? That's one of the most important things a database can do is store data. If your database loses data, it's not a very good database. So what I want to do is I want to talk about the ways that different databases guarantee durability. And so to do that, I want to actually talk about I want to talk about what's called LSM tree databases. And I'll be honest, when I first wrote this out, I was like, okay, I know a bit about Cassandra. It's one of the databases we use at work. I know how it works, the writes and reads can work internally. So it was a good one to talk about. But when I researched it a little bit more, I found out that Cassandra is actually not really unique. So a while back, Google released a white paper called Big Table. And apparently there's a whole class of databases that all work pretty much the same way. So Cassandra, I think HBase is one of them as well, LevelDB, a few others. So it's going to be interesting. They all use the same kind of model to handle writes. And this isn't meant to be a presentation on digging into the internals of LSM tree databases or Cassandra or anything, but it is important to understanding this notion of what Kafka is meant to do. So let's talk about this for a second. The write path is basically the series of actions that happen when a write comes into the database. So for something like Cassandra, the first thing that's going to happen is your write is going, well, actually I take it back, it's not the first thing, but the first part that happens in kind of this phase of the write process is your write goes into an in-memory structure called a mem table. So there's a couple reasons why you would write to memory first. I mean, one is that writing to memory is fast, right? It's an order of magnitude faster than writing to disk. The other reason has to do with some of the internals of how these LSM tree databases work. So you've got this notion of an SS table. So periodically what will happen is you have these mem tables being created, being written to as writes come in, and periodically they'll be flushed to disk as an SS table. But those SS tables have to be sorted. And if you think about sorting a data structure, it's going to be much more feasible to do that to a data structure that's in memory versus one that's on disk. So that's sort of the reason why you have this mem table structure. And essentially when reads happen, it'll check the mem table, and then it'll check all the SS tables. So the SS tables kind of get generated, and they sort of form a layer, and then compaction happens, and they get combined, and then new layers created. It's really interesting, but it's also not quite what this presentation is about. But I think the relevant part for us is the question of how does this system guarantee durability? Because what's the problem here? What happens? What's the problem? Or what's the problem in relation to durability of the system? Does anybody have any ideas? What happens if let's say this node loses power or goes down? What happens to that mem table? Well, I mean, essentially, what's that?
Yeah, flush, yeah, pro.
Yeah, exactly, right? Anything in memory is gonna go away. And granted, your database might have some mitigating functionality. Maybe it can talk to the other nodes that haven't gone down. Maybe it can recover that data. But hey, maybe your entire rack went down. Maybe your entire data center went down. So it's not a great idea just to rely on the rest of the cluster to guarantee durability. Instead, the way that these LSM tree databases guarantee durability is actually pretty similar to the way that relational databases guarantee durability, and maybe others too. I don't really know. I mean, I know relational ones that LSM tree ones built up the same strategy. And that's right too. I mean, it says commit log, but essentially there's a lot of different names for the same sort of idea. Commit log, write ahead log, trans log for elastic Elasticsearch, I believe. But the idea is you're writing to disk sort of a quick record with the minimum information you need to represent that write. So in other words, like if you lose power, you use this mem table. This commit log is all the information you need to replay the writes onto the mem table and to recover that data that you might have lost. So your durability for these databases is in a large part related to how often this actually gets written to disk. Because actually what happens is that like you're actually technically writing like the file system cache, and then that gets like synced to disk every so often. But that's essentially your durability guarantee, is how often this gets synced to disk. So that's important for us. It's an important concept to know for Kafka, this notion of the log, because Kafka is going to follow this idea. Sorry, over that. Going a little bit. So I do want to talk about the write-ahead log a little bit more. It basically covers what I was saying a second ago, which is just that it's a common strategy. CL tree databases like the standard doing it. Elasticsearch does the same thing. Relational databases like SQL and Postgres do the same thing. You have this log, and it's slightly different for like relational databases. I think most of them are based on B-trees, which is sort of like binary tree, but with like more branching factors. And there's this danger where like when you're updating one of the nodes, if you lose power, your database can be in a corrupted state. So you need once again this log to be able to ensure that your data is not going to get corrupted. So the point that I'm driving at here though is that like the log's really important. It's an important structure to almost every database that we use as programmers. And that's going to be important to understanding Kafka. But first I want to take a closer look at the log and talk about like what is a log. What is a log is like kind of a pure data structure. So the log is essentially, it's an append-only sequence of records, right? And the nice thing about talking about a log is there's not really a lot to tell. Like it says simple data structure. It's literally like a list of things. I don't actually know whether you call it ordered or unordered. I mean, its ordering is essentially in the in the sequence of writes. Like you get data back in the order that you wrote it. So it's a fairly simple idea. Like the drawback is that like you only get data back in the order that you wrote it. So querying not so much. But in terms of the benefits of this data structure, well, it's fast, right? If you're writing sequential data to disk, especially back in the days of like spinning disk drives, like the head of that drive has to like find the spot that you're writing. So if you're writing to sequentially, it's not having to seek around to find the spot that you're writing data to. I think with SSDs, it's probably not quite as beneficial, but I'm sure there's still some benefits there to having sequential reads and writes. Besides the speed, it's also a really simple data structure. And I feel like when you're talking about like distributed computing, it's much easier to scale a simple model than it is to scale like a Rube Goldberg machine that's like, stuck together with like duct tape and baling wire and stuff. So this notion of log, I think, if we believe that simplicity is easier to scale, I think that this log is very, very scalable. So that's the log as a pure data structure. I want to take this a step further though. And what I want to do is I want to think about like what if we took the log and what if we made it a database? Okay, so like in other words, like the log forms this like important component of the databases we use, but what if we just like extracted it out? Like what would the log look like as a database in and of itself? Well, it would offer certain advantages and certain disadvantages, right? Like we talked about some of the advantages. It's fast, it's scalable. Another advantage that we didn't talk about is that it's really good for replicating data. If you're running like a relational database like MySQL with like master-slave architecture, the way that it's getting data between the two is essentially a replication point. And if you're trying to diagnose issues and you think that your data is falling behind on your slave, then you just check the position of the slave on the replication log, you check the position on the map of the master, and if there's a discrepancy there, then you know that there's a replication lag. So we know that it sort of fits that idea of scalability too. Like you can essentially get data in and out like really quickly, practically at the speed of the network. So it's scalable, it's fast, replicates well. What are the disadvantages? Well, you literally can't do anything useful with the data, right? Like, you can't take the data and say, oh, okay, this is a log of customers. Give me every customer that begins with the letter F, whose name begins with the letter F. I mean, you can't do that with a log. Well, I take it back, you could, but you have to literally read every single record for every single query you want it to do. It's an extremely inefficient data structure. So that sort of stymies us for a little bit, at least in terms of our understanding of Kafka, because, or maybe our understanding of what role Kafka can play in ecosystem or architecture. But I think if we introduce one other concept, maybe make this all work. So what's the other concept? The other concept is a materialized view. So what is a materialized view? Well, in your database, you're going to have certain tables that you're responsible for managing, right? If you have a users table, that users table is going to get data into it by you writing rows to the users table, right? If there's an orders table, let's say. You've got to write data to that orders table if it's just like a plain table. But there's this notion that some databases can do, this idea, this functionality, called a materialized view. The materialization part of materialized view means that it's actually stored as a table. This is an actual table on disk, so it's not much different than like your account or your users table or what have you, your normal tables. But what is different is that you don't write to it directly. So materialized view, that's the view part, is essentially derived. It's a derived table from your base tables. So it's kind of interesting, and it's something that some databases will do for you automatically. So it means that, like, let's say you have like orders and you have accounts, and your accounts have zip codes, and you want to like have an aggregation table that's like, I want the number of orders by zip code or something like that. You can set up a view so that your database, or some databases at least, could calculate that automatically for you, keep it in a table in the database that you require. I mean, there's disadvantages too, right? Like, it means that every time you write to the account table or the orders table, it's going to have to perform 2 writes instead of 1. So, I mean, there's definitely performance concerns. But it is an interesting idea. And the reason it's interesting to us is that you have, in this, you have the notion of the source of truth. And I totally stole this picture from, like, the internet. And I wrote some of these, I diagrammed some of this stuff out on this chart, but some of it I just shamelessly stole. And this is one that I stole that is actually really well suited towards the, the point I'm trying to make. So anyway, so we had this notion of the source of truth. What's the source of truth? That's the data that, like, if that goes away, you're in trouble, right? Like, if you lose the source of truth data, that data is gone forever. Whereas your materialized view could get blown away, and you could always rebuild that materialized view from your source of truth, right? If you have the orders, you have the users, you can rebuild that aggregate table. Which isn't to say it might not be catastrophic. Maybe you have some core business process that's like depending on that materialized view, and you're in trouble, and maybe it takes a long time to rebuild. But the idea is you're not losing any data as that materialized view goes away. So that's an important distinction. Our source of truth versus the data that's derived off of that source of truth. All right, you guys ready? So this is the moment that for me was pretty mind-blowing. And it may just be that I'm like easily amused by things or easily like impressed, but to me this is the big reveal. This notion of turning the database inside out. So what does that mean? Well, it means like what if we had this like notion of like this log, this distributed scalable log that we could treat as our primary data store, our primary database that held the source of truth, right? So the records in this log are the records that we carry. This is the source of all of our data. Well, if we had that, then one thing that we could do is we could take other database technologies, use that centralized log, and stream the data from the log into these other databases. So the other databases become not like we typically use like MySQL or these relational databases for. They become essentially materialized views. They're not the source of truth, but they are built from the source of truth. And to me, that's a really cool idea. It's really compelling because it means that like, hey, if you do full text search on orders, you just pipe orders into Elasticsearch, and you have full text search. But you're not responsible for like this like ETL process where like you have to make sure you're manually like pumping the data in. Like, it's all something that happens reactively, which is really neat. In high scale, low latency queries with Cassandra. You discover things about your data, use MySQL. So you can build this whole system of polyglot databases that are all sort of reactively receiving data from this sort of centralized distributed logging. And in this model, in this architectural model, I mean this is Kafka, basically, is that distributed logging. And Kafka, the streaming architecture you can build around it can essentially build this architecture. So I think it's really cool. Personally, I really like, when I read about that, I thought that was a really compelling sort of idea. There's a great article called Turning the Database Inside Out, actually. I think it's not only about Samza, but that's like it's related to Kafka. So anyways, I do want to stress, like, this is sort of the centralized, or the central sort of architectural idea I want to play with and I want to build on and explain. It's obviously not the only thing that you can do with Kafka. I mean, Kafka serves a lot of different use cases. Honestly, like for my project at work, I think the biggest appeal of Kafka was just it was a like standardized way of getting data from one place to another. We had a couple of different mechanisms for doing that, and like it just doesn't make sense to maintain multiple mechanisms. So Kafka is not, I mean, it's not like you have to build this system off the bat, right? This is a really cool idea. It's a really cool way of structuring your system. It's not something you have to do. But I think it sort of exposes effectively like what Kafka is. So this is just some of those other use cases. I mean, one of the nice things is regardless of like what you're doing with the data, Kafka gives you a nice centralized place to put the data. I feel like when you're talking distributed systems, there's always this dance between centralization and distribution. And in this case, like having all your data in one place essentially allows you to scale more effectively. If you can pipe that data to multiple different locations. I think you could maybe make an argument like, oh, well, isn't that what we use like relational databases for? Or isn't that like what integration database is for? But I think that the differentiation between using something like Kafka as your centralization point versus like a relational database is, one, Kafka scales a lot better. Like if you start really scaling like relational database, you're gonna have to deal with sharding and replication and all that stuff. It's not much fun to maintain. Whereas Kafka handles that scale pretty seamlessly. I think the other thing is just that when you're dealing with like a relational database, you're essentially talking about amplifying the data, right? Like if you're exposing an object graph based on a relational database, like people are going to use that object graph, which is okay in some instances, and to some limit. But especially if you're in like microservices architecture, you don't want people just like using the entire object graph without limit, right? You want them to limit themselves to the data that a service exposes. So that's another reason why centralizing around like data plane versus like an integration database is maybe a better decision for a scaling system. You can use this for pub sub messaging. That's kind of important measure for microservices. Like you have an order service that in order to complete an order has to call the inventory service, the warehouse service, the shipping service, et cetera, and they all have to call their services. It means that if one service goes down, you're kind of screwed. So you don't want to have to like have this notion of choreography where like the one service dictates the entire process. It's a better pattern, a more scalable pattern to have a reactive system where you emit events and sort of react to those events. Yeah.
What's the event trigger? Event trigger?
Event trigger?
The event trigger.
You need to have a trigger right for the event.
Oh yeah. So you still have one service that's writing the event, right? So like the differentiation is that in the first model, the order service is calling 10 different services, right? In the second model, the order service is creating one event in response to whatever, like a call from the front end, maybe the customers like ordered a product or something.
So I guess the recommendation is to have a Kafka log per data entity, you would say? Like for example, you have a customer service and you have a product service. So you have a different Kafka log for each one of those entities?
Yeah, and we'll talk about that actually in just like a couple slides. Okay. But yeah, it's essentially they're called topics, but yeah, we'll talk about those. This is basically just to show that like while this big reveal or whatever is like a cool idea, you don't have to like go all out just to use Kafka, obviously. The other thing is that it does simplify the architecture, having sort of like the data plane. And this is kind of a cool example to show, which is, this is linked in before Kafka, this is linked in after Kafka, much prettier architecture on the right. It is worth noting that LinkedIn created Kafka, so it was designed to basically solve their problems. So it's probably not completely surprising that it like makes everything work really nicely. But yeah, so that's kind of my pitch behind like I guess the idea behind Kafka and the role it serves in the architecture. So for the rest of the presentation, I want to do essentially two things. I want to talk about like the broker itself, which is that log structure, and then I want to talk about the ways that you get data in and out of your out of that log. If you wanted to populate this materialized views, or if you wanted to, I don't know, like do whatever. I mean, you could just do data enrichment, package data to S3, or package the data lake, or whatever you're going to do with the data. You need separate clients to like get that data in and out. So the first thing I want to do, and this is kind of crazy, like it's not meant to be scary. I just want to point out that when you're running this stuff in production, like there's a lot of different pieces that you can use, and you don't have to use all of this. This is the reference architecture that Confluent, which is the commercial company that's basically like the guys at LinkedIn who created Kafka, left and founded a commercial company to offer like enterprise solutions like based around Kafka. So this is their suggested small cluster architecture. And the reason I bring it up is because I want to point out that what we're talking about is just this layer right now. Like all this other stuff, you have some utilities around managing schemas if you're writing an Avro. I'm not really going to talk about that, but it's worth looking into if you're Kafka. You've got different clients, like these are meant to be clients. KSQL is going to talk about that. But for now, we just want to focus on this broker layer. This is that distributed log essentially. And there's a couple of different components. This rebalancer, if your company's got the money, maybe that's something you can use. We're pretty cheap, or what's the word? We're pretty yeah. Anyways, we don't spend all so we use some free version.
You can say it, and I'll bleep it in the video.
Yeah. So anyways, the two parts that you will use though are the Zookeeper part and the broker. And I just want to point out you don't really need to worry about Zookeeper for now. It's kind of like a clustered technology for doing low-level distributed operations. Kafka uses it for now, but there's plans to phase it out in the future. So just know you gotta run the Zookeeper cluster to run Kafka. You can even they recommend the small cluster architecture just to run Zookeeper on the same nodes that you run Kafka broker. But like I said, I don't want to get too into that stuff because it's complicated, especially if you don't have a background in Kafka, it's scary. So I think we should go back to these nice predictable diagrams. So let's talk about the way that Kafka, the log is organized, right? So sorry, is this too loud by the way? I feel like I'm echoing.
No, actually you can pull it up a little because there's a background white noise there. So.
Okay, so the first level of organization you have is a topic, right? So a topic is just a discrete message channel. It is a separate channel you can send events through, or messages, or records, whatever you want to call them. You're sending it through those. And it's important to know that when we're talking about the broker, so in other words, we're not talking about clients, because clients can do some enforcing of schemas and stuff like that, but the broker does literally not care what you put in. Broker cares about topic organization, but it says, hey, if you want to put, this in, if you want to put this number in this topic that it's expected from JSON or whatever, it's fine. It's all bytes to Kafka. So, these topics, they don't enforce schemas, they don't enforce data types, they don't really enforce much. What it does is that the topic is the smallest unit that you can configure separately. So in other words, we'll talk about replication and stuff like that. You can set different replication vectors on different topics. But like we were talking about earlier, you would maybe have a topic for orders and have a topic for shipments, and yes, you kind of organize your data around this way of topics. That's sort of a higher level organization you probably use as a developer. But the next thing I want to talk about, I think is pretty interesting, is partitions. So partitions are essentially how the topic gets divided up. So when you create a topic, you define how many partitions you create. And so you're responsible for figuring out what makes the most sense. Now the thing is, partitions affect scalability, because ultimately all of your partitions partitions have to be divided up amongst the different brokers. You can't split a partition in half or something. I mean, you can define more partitions for topic, but so like in this example, like you might have a client that routes different messages by their key, like maybe it hashes the key and it uses that to divide it into partitions. Once again, I don't believe the Kafka broker actually cares about that. I'm not as certain about that, but I'm pretty sure like it doesn't care about partitions. That all happens at the routing. I think that all happens at the client side. But the idea is like if I have this two broker cluster and I have 4 partitions and I add a third broker, like what's going to happen? Well, one of these partitions is going to go to the third broker. We have like one instance with 2 partitions and 2 with 1. If I add a 4th broker, you know, like it'll balance out again. And to some degree, if you're not running like the fancy paid version, you kind of have to do this rebalancing yourself. You know, which kind of sucks, but there's command line tools that you can use for it. But if you add a 5th broker, what happens is basically nothing, right? You can't divide 4 partitions amongst 5 brokers. So at the very least, you have to have a sense of how many brokers you're planning on running, and sort of base your partitions off of that. And you know, if you're planning on eventually growing your cluster, you've got to make sure that you have enough partitions that you that you can fit onto all of your future broker nodes. Yeah, so that's basically how Kafka takes a topic and divides it onto its brokers. Question? Yeah, so well, maybe one thing to point out would be, that is, I mean, that's essentially what the partition is. So if you think of a log as like one big series of sequential writes, like a partition is chopping that sequence up into smaller parts. So that affects ordering, and actually I'll talk about that in a later slide, that you sort of lose some of your ordering guarantees. Oh, so this is for each topic. So I should have probably pointed that out. Each topic is divided into a number of partitions. So if your topic is like 10, let's say you have like an orders topic and it's got 10 events in it. So that means like, maybe 2 events goes here, 3 events go here, 3 events go here, 2 events go here. So it's like as your client writes the events, it'll route each event to a specific topic. Does that answer the question, or?
Then I'm just trying to make connection between the data structure visually with this architecture.
Yeah, I mean, I think maybe the way to think about it. So like pretend this is like a log, right? Like this is a sequence of writes essentially. Like the first record in your log is 1 with some. This is meant to be JSON, by the way. I didn't want to like fill a bunch of dummy data and make it really big. Pretend this is some JSON object with some, order name, your product name, order ID, whatever. So think of this as your log. Like this is the log data structure. If we're not dealing with like partitioning and not dealing with distribution, it's just like a series of records. So we're sort of this, where Kafka differentiates from like a normal log is that it's not just one series of records. It's one series of records that's divided up into several different sort of mini logs, I guess. Like each of these is a log. So your topic gets divided up into multiple logs, I guess you could say. But yeah, so for each topic you might have different partitioning depending on how much data is flowing through and a number of different factors. So any other questions on the partitions? So the other thing that partitions are important for is that you can replicate. You replicate on a per topic basis. So if you have really important data, you might want to replicate it, like 3 times or 5 times, whatever it is. Typically you're guaranteed not to have data loss if you lose less than your replication factor of instances.
So in a stream, right, it has a TTL per se?
It can. So that's another thing I guess we could mention is that you can absolutely set a TTL on your stream. You don't have to though. And actually, so that's
it can't be persistent.
Yeah. That's what's that?
It can't be persistent, right?
Well, it can. I mean, depending on how much data you throw out there, right?
So for you to have a business logic, to have like in a PubSub, the data comes through a publisher event process. and you're consuming the data, and you need to process that information to get some value out of it, business logic, because the data that may stay there may be stale because the subsequent data coming in a different context within the same topic could override that information. You understand where I'm coming from? I mean,
Yeah, I think so. I think so. I
there's
mean,
an order. You just said there's an order.
Uh-huh.
The order has to be fulfilled,
right.
and you need to package and deliver, right?
Yeah.
And make an invoice and make sure that your stock is available. The order has maybe another topic called inventory, right? The stock, the order has to meet the inventory criteria so you can complete the process. So if I'm relying on an inventory topic to fulfill the order, and I'm getting another order with the same inventory item, right? I may run out of stock. So,
Yeah.
I mean,
No, I mean, it's right.
in an
Like,
abstract manner.
from what I've heard, ordering is one of the things that does occasionally become an issue. But I mean, I think if you think about, like, let's say you have a stream of order entries coming through, like for each of those orders, like you're still going to process them. You're still going to be able to check.
I mean, is there, when you say that, hey, this topic becomes stale, this data, is there, that's why I'm looking at the TTL, right?
Well, okay, so what if you had like your inventory service and it's processing orders, right? And it's updating some data store as it's processing. Then I think what it has to do is it's got to check that same data store to make sure that there is inventory before it can guarantee that the product goes out.
Yes.
Yeah.
I think you're looking at a problem that is more of a distributed. There's another problem. But I think that's more of an distributed system, asynchronous system problem. Not, I mean, Kafka is just a means to an end. But I mean, you can have that problem, the same problem with any type of middleware.
Yeah.
Yeah, but it's not asynchronous. It can be an asynchronous process event per se.
It's not real time, right? It's not a synchronous call where you're just doing all your transaction with multiple like inventory.
Right? I mean, your classic example I look at is, there is a chart of data coming in. User is going through a change in their, position, and the HR3 data made a mistake in terms of the cost center code. And the next data comes in, and I need to process this whole cost center code and update what are the downstream subscribers who are consuming the data, right? The next data comes in, is it going to be what then it becomes a FIFO, LIFO challenge? How should it be processed in a specific, employee ID context? Do you understand the TTL component where I'm coming from?
I think so.
Yeah, I mean, so there is an employee ID, the employee went through a job code change, a cost center change, and the cost center process data should be processed and replicated to the subscribers. And there are various different subscribers looking for the data. And then the next event comes in against the same employee ID with a different cost center code because the data was wrong.
Right, but I mean, like when that second event came in, you would update whatever store that you're.
Yeah, so that's last.
I think there could be race conditions, right? Like if you had the two events that were generated around the same time and they got set to different partitions, like you would absolutely have race conditions.
Okay.
In fact, when I've talked to people about like running Kafka, that's like giving interviews or something.
So the business logic of race conditions are not built into Kafka, but in your app.
I think it's part of the eventual consistency too, right?
Right.
I mean, that's always a risk. I mean, but yeah, there should be something in the middle that is going to guarantee. It's like, for example, when Amazon, just meet another in Amazon.
There's some sort of business logic to evaluate the conditions, per se, as part of the
I do know that part of the message that gets sent, like the structured message, I believe has a timestamp that can be like generated by the brokers. So you could do some like manual like checking. I think the race condition is probably the bigger issue because you can structure your processing as like a directed graph or something, right? And like, kind of like reactively.
When you start talking about partition and stuff like that, how do you keep the data in sync and how the data can be distributed to various partitions?
If it's that critical, you could always have a single partition. And then you would guarantee all messages in
Yeah.
situations like that. Multiple partitions partitions are usually when you have a lot of requests coming in that are independent, like from a web server.
Yeah.
Look this up, look that up, then you partition it out. You have a whole
State.
bunch of things.
So because the condition is the state, right, there is a state component involved.
Right.
When you have a state component, then you need to be careful about how you're positioning, how you're distributing the data, and then the question comes, around ETL, right?
Yeah, you
Well, I mean, you have
absolutely
stale data.
If you need to preserve order, you have to use a single order.
Okay.
Yeah. You can still replicate it, so you got fail, so you can back up and all that. But then you would be guaranteed to get all the orders.
But then you won't use Kafka.
Yeah. I mean,
But
there is a
you're paying a
solution.
big price of using Kafka for having a single partition.
Yeah.
I've heard that though. Some people like certain use cases will just have this, partition. So,
I
people
built
do.
a big pub cell,
yeah.
and that was exactly it. We had triggers on the input side. Every time there was a change, it pumped it in, but we had to maintain order.
Mhm.
So we would have a single partition, it still worked great.
Yeah.
Because it would have 10 subscribers, and each one could go through with the speed they could process.
Right.
And pull out all the changes.
Right. That makes sense. Yeah, I mean, like, I've definitely read some of, like, the conflict materials they put out, and I remember, like, reading that they said that with the caveat that, like, obviously it's not quite as scalable to do it that way, but yeah, I mean, absolutely.
Distributed systems.
Yeah. You can just use a RabbitMQ.
Luckily, the use case that we're dealing with at my job is, like, it's pretty much just one-way processing. Like, we don't really care about, this sort of, like, race conditions or anything, so, I mean, obviously, like, more complex use cases are more complex. Oh yeah, so we were talking about partitions and how they affect replication factor. So essentially the way that Kafka handles partitioning in terms of replication is that your leader partition is going to handle reads and writes. But you do have follower partitions, however many, like just to satisfy your replication factor. And so there's failover built in. If you're, one of your leader of a partition goes down, your broker that's got a leader partition goes down, and it'll switch over to one of the follower partitions, which is nice. And then gives you time to, prepare, bring the node back up. Okay, so that does bring us to persistence, because that was something worth talking about, which is that, I mean, if you have replication, obviously, like, unbounded data growth is like a problem, right? You're streaming a bunch of data through, and there are some topics you're not going to want to, like, keep around forever. But the idea is that Kafka can be a database. Like, there's no reason that you couldn't use it as a persistent data store. Like, if it has a replication factor, I mean, there's no difference between that and, like, say, what Cassandra is doing. The data is backed up. You can handle failures of brokers. It's secure. It's not gonna, you're not gonna lose data if you keep it in Kafka. But yeah, we talked about TTL persistence. You can absolutely set events to expire and not keep them in the broker. Maybe it makes more sense to stream your events to S3, as a backup or something like that. That might be more effective. And then if you ever need to reprocess them, you could just have a consumer that pulls the events down and puts them back through some like replay topic or something like that. And then there's also this notion of compacted topics. So if you had like a topic that was like maybe like users, and every time a user changed, it would just like put the entire user object into the topic. You could have topic compaction where basically Kafka would go through and in a background thread every so often, it would essentially just go through that topic. And like if you had a more recent event for user 10, let's say, and you had an event for user 10 that was further in the past, it was no longer like relevant, it was no longer reflected like the most recent state, it would like clean up that event and delete it. So that's one way that you can kind of deal with this like unbounded growth problem. Although it's not applicable for every topic and every use case. So I think it's, one other thing. So this kind of gets back to that idea of like, the problem with distributed systems, which is that if you have a single log, right, like we're talking about with like, if you just had one
partition.
You just have one partition, it's not a problem, right? You know you're going to get the events in the order that you wrote them. But if you have multiple partitions, you might have different processor applications that are getting those partitions separately. In which case you can't guarantee that, like you can guarantee event 3 is going to get processed before event 4, you can't guarantee event 3 is going to get processed before event 7. So yeah, I mean, like, buyer beware. If you do have strict ordering requirements, like Kafka is, like we were saying, you might have to run a single partition, you might have to use a different technology that can guarantee you that ordering. So you do lose ordering guarantees with Kafka. So that's it for the bit about the broker. I mean, hopefully that gives like a little bit of background and insight into how the broker itself works. How are we doing on time?
Okay, well, around 10 minutes.
I had to burn through one more time. Okay. Alright. I feel like not only did I not get to the coding demo, I don't know if we get through the actual slides for sure. Anyways, that's okay. We'll try to get through as quickly as possible. So the idea is, okay, so we know like how data is stored, how we organize our data, so this is how we get data in and out of the cluster. So the first thing to cover would be the notion of consumer groups. So this is that idea that if we're using the architectural model of, hey, we want to have this distributed log, we want to then pipe all that data to multiple destinations, we need this notion of pub sub. What we're really talking about is kind of like pub sub, but with like optional persistence, right? So that's essentially what the consumer group is if you have a cluster of applications, you're not going to want to just use one application to process a topic, right? You're going to want to run a cluster if you're running at any sort of scale. So you basically just, in the configuration of your clients, you say, hey, this belongs to consumer group, ship it. And then Kafka will automatically ensure that those applications have the data divided amongst them. To be honest, I don't actually remember if there's a limit of like one partition per application or not, or if it just sort of sends the data out. But at the very least, you know that like the entire data set is going to get divided amongst all of the applications within this consumer segment. So this is sort of just a kind of contrived example where like you've got a restocking service and a shipping service, and they both care about orders, and both are going to get a full set of your data. Pub sub, pub sub. So with that in mind, that's how client processing like works. It's how the data is divided. I wanted to kind of just do a quick review of the different clients that you have available. Because essentially when you're choosing what client you want to use, you're choosing a level of abstraction. So at the very low level, you have like producers and consumers. And these are the ones that are geared around, like the producers geared around like single message creation. Like I want to create a message, I want to maybe attach a callback to it, and then like the producer will kind of like take care of all the rest. It'll do the partitioning and the routing. Like you don't ever work with partitions for the most part. I forget whether the producer does support it or not, but like for the most part, you're just going to say like, hey, partition, here's the message, like send it off. But if you want a richer processing model, you want to do functional transformations on your data. You want to use stateful processing. You've got to use like the streams DSL or higher. There's also something called the processor API. To be honest, I'm not super familiar with that API, so I can't really talk about it with any sort of like knowledge. But I do want to at least mention that it's there. I think it's a little bit newer, but I know it's supposed to be a little bit higher level, I believe. So maybe just to give a quick sort of like illustration of what the difference is. So the producer API, you can see like you're building the record manually, you're sending it out, like you're sort of working with the entire thing. Whereas with the streams DSL, you're working with the entire stream. And so like you can see there's sort of this notion of like functional transformation. You can join streams together, you can do windowing, you can do a bunch of different like operations like that you wouldn't be able to do with like a consumer, let's say. Producer consumer, the consumer like reads data, but it just reads simple batches of messages, and the producer writes data. Whereas the streams, I guess the other difference is like typically the use cases, like producers, like when you're getting data into the system, most people use a producer, and then most people use streams for like enriching the data. Like if you need to take a topic in, do some sort of transformation, and then create a topic out, or create like a materialized store that you can query or something. Like that's usually what we use streams for. A couple other topics clients worth noting. Kafka Connect. So in the architectural model where we have data being piped to databases, you could certainly roll your own and then have to maintain your own, and like each time you want to add a database that you want to send data to, you've got to like do that. But you can do it on your own. Like there's nothing special about it, right? It's right roasted database. But there is this sort of like framework that Kafka provides called Connect. You can say like, hey, for every order in the order topic, like just automatically read it to MySQL. And there's some like configuration you can do. Honestly, it's kind of a pain to set up for that. But like we used it in our use case for like S3, and that wasn't too bad to set up. It's fairly straightforward. But yeah, it just automatically writes events to the data store. So that's sort of used on the tail end. But the other thing you can do is it does have a sink as well, or a source as well, which is pretty cool. So if you guys have heard of like change data capture, to kind of bring this around actually full circle, the idea is that you can have a Kafka Connect source that will watch the write-ahead log of a database, and it will generate events based on the write-ahead log, which is kind of crazy. Like, if you wanted to watch the users table, every time a user's updated, it'll send a user event through the stream. So it's a pretty neat idea. And then a couple others, KSQL, it's like Kafka Streams for transforming streams, but with a SQL-like language. It's running clustered mode, same as Kafka Connect. Like you have to have clusters of Kafka Connect and a cluster of KSQL, because it is doing pretty intensive processing, depending on your scale. And then REST proxies for non-Java users to do data through HTTP. Just about out of time, so here's it's the best diagram I can find. It's not great, but basically it's kind of like illustrates the different use cases for all the components. You get data into the cluster with, like, say, Connect source or producer. You do data transformations with Kafka Streams and KSQL. Take actions via Kafka Consumer. If you have a side effect, or send out emails, whatever, and then Kafka Connect Sync is that part that sends it into the materialized views. We're just about out of time. Let me at least mention that. I guess the other interesting thing to do or to talk about with Kafka Streams is that it allows for stateful processing, which is something that like traditionally you weren't really supposed to do. Like there's this like thing called like 12-factor apps. It's like manifesto that defines like good architectural principles, and it's pretty big in like the microservices world. And one of the principles is don't have stateful applications, right? Like, applications should run anywhere. They should be easily portable. And so Kafka kind of turns that on its head. And I feel like Kafka kind of lives in this gray area anyways, where like, does it belong on the sort of like application layer? Does it belong on the data engineering side? And it's kind of in the middle, I guess. Okay. I was still like pretty close to the limit, so I'm gonna keep going for a minute or two. Because this is a really cool idea. So one of the things that sort of powers a lot of this stateful processing is this idea of the stream table duality. And I want to at least cover this because I think it's a really cool idea. And I like to geek out on this stuff. But the idea is if you have this stream of changes, right? Okay, can I do one? You've got a name, you've got a status. The information present here, not the historical information, but the end state, if I process this, is actually equivalent to this table, right? Like if I process all of these events, like the information I'm ending up with, right? Like because this last event is changing the status of account ID 1, it's actually equivalent to this table. So the stream table duality is this notion that any table can essentially just be seen as a materialization of a stream of changes, right? A stream of deltas is essentially equivalent to a table, which is a really cool idea. And it means that you can take a stream and you can build a local on-disk data store, and Kafka uses something called, well here, let me actually go switch there. Kafka uses something called RocksDB, which just to bring it around again is actually an LSM tree database, so it functions with that mem table, with the SS table. So anyways, it uses RocksDB. You can do it in memory too, but you can actually store on each Kafka Streams application, it'll store the table representation of the partitions of a topic that had been assigned to that Streams application, which is kind of crazy if you think about it. Or if you need access to the entire data set, you can use a global K-table, which rather than just storing the materialization of the partitions that the application's been assigned, it can just store the entire data set. And so essentially you just treat that as like a local database table that you can query, which is really crazy actually, but really cool. And so I guess the other thing to point out would be that you can kind of do the same thing. A K-table it's literally a topic that's materialized, whereas a state store is the same idea. The only difference being that like rather than directly materializing to a table, you actually like enrich the data and then you materialize enriched data that's not necessarily directly from the topic. Although it's almost identical in the sense that if you declare a state store, Kafka will create an internal topic to back up that state store. And the last thing I'll say about this is one of the concerns, right, is like, hey, if I have like stateful processing and one of my applications goes down, that means I have to replay all that state, right? And that sucks. And that means that your processing gets slowed down. You have ordering issues because like one application is far behind. So the other thing that's worth mentioning is that actually that whole replication idea comes into play where the followers of a partition will also build the state stores and k-tables, so that if your streams like processing application goes down, that there will be some backups that can like pick up the processing immediately. They'll already have the state store and k-table on there. I think that's configurable. I'm not really sure exactly, but I know that that is definitely a thing that is true. So yeah, I mean, I think, is there anything else? Maybe window joins is just the same kind of idea. Rather than materializing as a table, you can just join streams to streams in like a windowed fashion. But I mean, hopefully that gives you guys a better idea of like what's possible with Kafka streams and the sort of processing you can do, the role that it could fill in architecture. Anyways, I mean, it's the stuff that I thought was interesting. Yeah, that's basically what this presentation is about, sharing stuff that you know, I thought was pretty cool. So.
Can you spend a couple of minutes, because I talked to you, I mean, when you brought this idea of talking about Kafka, that you were doing this implementation at your work. Can you talk about a little bit about the use case at your company and the problem that you were trying to solve by doing this?
Yeah, ironically, the big motivation was actually just that we were using Kafka a little bit before. So we were using an old version, and we were using Kafka but as a direct drop-in replacement for SQS. So SQS is like Amazon's queue service. So we were using it to like essentially get data from one server to another. But I think my biggest motivation actually at the time for pushing Kafka was the data plane idea. To me, that was actually like the more practical. I mean, like the whole like materialized view thing is cool, but like the data plane I think has the most value in that like, okay, rather than having this channel of data that's only for this one use case, right? Like okay, we need data pumped from like our API server to like a server that does other processing. To me, the bigger win was essentially not having single use case like streams of data, but rather having data that was, you know, independently useful and reusable. So we had to restructure our data a little bit so that rather than creating like data streams specifically for one product, we sort of made it generic and then made it so that like, you know, like essentially to support PubSub. But the specific use case was basically has to do with like data insights, like actions that were taken by customers that then we would run like content enrichment on those actions. So essentially, we didn't do any like really fancy stateful processing. It was mostly just like running business logic on events that were coming in. We did, yeah, I mean, we would have an event would come in. If it didn't have associated content, we'd run it through this like content extraction process, which would then update like a standard table. Not really using like Kafka Connect or anything for that. We're doing it kind of old school, but you know, maybe one day more like Kafka Connect stuff.
So you were using SQS. So I'm assuming your cloud provider is AWS. Did you consider Kinesis instead of using Kafka? I mean, managed service versus standing up your own.
I mean, I think cost is always an issue. I think it probably would have been fairly equivalent for like our particular use case, but I think if, you know, like our plan is to lean on it more and more as a centralized place that you can put data and then you can take data out. And I think the feeling was that we would, you know, over the long run, like the cost would be more beneficial to manage it ourselves. I mean, and once again, like we're pretty scrappy, I think is the word I was looking for earlier. We're scrappy. That's how you say cheap when you're trying to do, you know, correct or whatever. But yeah, so I don't know, any other questions or comments? Okay.